Well, good morning or good afternoon, wherever you are. This is not the first time I've had the opportunity, the privilege to present the closing keynote address at ISC. But needless to say, for myself and all of you, this is very, very different. This is the 17th year I've had the opportunity, the honor to make this presentation to ISC. It is a personal opinion piece, a personal editorial of what's happened over the last year in our field. And as many of you know, I tend to be a little bit more hardware oriented usually, but this is not usual, as I think we all know. And so I will be mixing more software, at least on the side of applications, with this. Every year, I try to find some pithy expression that captures in one or a few words what the last year is. This was not easy for this year, because this year is like no other year, certainly in my lifetime, and I suspect in most of yours. I chose a world in hope, because wherever you are, I think that you and we are experiencing the same sense of need for a future that is better than our present. And more sadly, many have lost their lives since I last presented on this virtual stage. And there are more than one different kind of worldwide dilemma, crisis, really. It is a health crisis. It is an economic crisis. And for those of us in the US, it is a crisis of conscience, long overdue. And all of these are together. So I'm going to try to represent that aspect of the last year within our field. I try to identify some trends that define the last year. There's no way to get around it. COVID-19 is the dominant issue, trend, challenge, and threat of our time. And what I hope to show is that to this challenge, we, the high-performance computing community around the world, are picking up our tools and applying them to the solution to this generational problem. And so, in part, I hope to capture supercomputing as it is being applied really as a weapon to address this really invisible enemy, this virus. And in some sense, in the back seat is the progress that's also been made, perhaps more invisible than usual because of all the other challenges, but for exascale. And I'd like to talk about exascale. It's an amusing contradiction that we're experiencing. Even as we approach, converge, possibly achieve exascale, the very nature or definition of exascale becomes more blurry, richer, broader. And so we'll discuss that as well. And also, AI, machine learning, deep learning, supervised, unsupervised, is become an even increasing driver for high performance computing, and in particular for the COVID-19 challenge that we are facing, and I'll touch on that. And then, obviously, this medium, ISC 20 has gone virtual, remote. And the very fact that I'm doing this now shows the success with which the team of international supercomputing over the many years has undertaken such a professional challenge as to make this conference possible to its fullest richness and informative aspects within this more restrictive, remote, virtual venue. And I have to tell you, frankly, this is a little different for me, and I'm trying to get used to it. So I trust you will bear with me and be a little forgiving, but there is useful information. So there's no point in putting it off. In the virtual rooms around the world, for those of you who are watching this, the elephant in the room is this. This slide requires no title. It has become the iconic image, perhaps the defining image of the year 2020. It is, of course, a visualization, a scientific visualization of the COVID-19 virus, also known as the SARS-CoV-2 virus. In the US, to which I've been most exposed, but also understanding the challenges, the earliest challenges in China, South Korea, in Europe, Italy, among other countries, and then in the US, as well now as parts of South America and Africa. Scenes like this have gone on in tens of thousands of places every day around the world. And many people have lost their lives. Just in the US, I believe that we are either approaching or have surpassed, I haven't checked in the last few hours, 120,000 people dead because of this virus, and perhaps in part because of our inadequacy or inability to address it in the most rapid way possible. This chart is from the World Health Organization. It is one of many. The principal reason is the red line, and the left-hand side of the graph shows the metrics here. And this is showing that the total cumulative number of cases since the beginning, this graph goes back to January, but we in fact know that the virus was at least incubating as far back as November of 1919. Sorry, wrong virus. 2019, just off by 100 years. And you notice, you can observe the red curve that shows the monotonically increasing number of cases. The other bars are the additional cases added per day in the different geographical areas. Yellow is the European, green is the Americas, and I believe that includes not just the US, but Canada, Mexico, and South America. And the gray covering the myriad other countries that either have or are now experiencing the same virus. And in that area, you can see that this represents the transmission of that disease to many other areas, parts of the world. this is more sobering, if anything. This is not the number of cases. This is the number of confirmed deaths on a per daily basis. And the black line is the world death rate, where we see that something on the order today of 3,000, 4,000 people dying every day. I guess the good news here is that number was more like 8,000 on a daily basis and has somewhat subsided. But, you know, if you're not ignoring the derivatives, in fact, there's a small amount of increase again in the world. These other curves represent a sample of different countries that have shown more of the cases in the world than the general overall populace. And this is no bragging rights, is it? The US has really exceeded any of the other countries in the total number, the worst number of deaths on any day, well above 2,000, almost 3,000. We are very pleased that that number is in decline, as slow as it is. And we extend our sympathies to Brazil, which is now surpassing even the US in terms of the number of deaths on a daily basis. And we observed that both India and Mexico are rapidly at this time increasing in the number of deaths per day. This is a very sobering curve. I might note, and I'm pleased to see that Russia, which did have a bad start back in April, has managed to overcome this transmission rate and at least flatline where it is. But the thing that this graph says to me more than anything else is that in spite of what some politicians in the US and others may say, that black line says that the pandemic, the coronavirus 19, is not gone away. And at the moment, it doesn't seem to be going away, at least worldwide. And with concerns about a possible second wave, this becomes even more deeply concerning. But of course, those curves I showed you weren't normalized. And so here's a set of curves, pretty much the same, but these are normalized against population counts of 100,000. And what I take away from this is the very different amount of deaths per unit population, depending on the geographic regions in the planet. In fact, the number varies approximately at least a factor of 6 across there. And I don't know if it's something to be pleased about, but at least the US isn't at the top of this number. Spain and the United Kingdom seem to have the highest density of cases at this time. Germany has shown a remarkable ability to limit, if not minimize, the number of deaths per population. My credit to Germany. I think Sweden has been very interesting to watch because they have taken a different approach, a herd immunity approach. And I'm certainly no doctor and I'm not going to pass judgment, but my sense is that perhaps it was not the optimal approach to take, meaning no disrespect to our colleagues in Sweden. The situation is so dark that I show this graph as an example of good news. more than 70 years ago. I was born in New York City, and I spent the first 20 years of my life there. This chart is from New York City, and it is the number of deaths on a daily basis for New York. And clearly, the take-home message is that New York suffered greatly at its peak. And through stringent measures, and I credit both the governor of New York, Cuomo, and the mayor of New York City, de Blasio, and they didn't always get along with each other, but by together applying control methods with the engagement of the populace mostly, we see that the number of deaths per day have diminished to, well, not quite, but almost zero. This is wonderful. I can't help but stare at this. I used to do some statistics, and this looks to me like a third order error log, maybe second order, but I'm going to call it a third order error log. And I'm sure there are some of you in the world of probabilities and queuing theory and so forth that actually know what the parameters of this error log is that can be related to the phenomena we're observing. So we're here, as we do annually, to explain, interact with, and in some ways brag about our field, the high performance computing field, the field with the fastest growth of any technology in human history. And here we find that we have set aside the competitive edge that usually attracts us to this conference, waiting for who's number one, Ichiban, right? And coming together, not purely by intent or organization, but by natural inclination internationally to address the challenges of this unique and painful crisis around the world. And I just want to show you a few examples. And my apologies ahead of time if I don't do adequate representation of all of the places in both hemispheres that are working to this. Our colleague, Satoshi Matsuoka, and a personal friend helped me. The timing of this meeting is very good. Satoshi, as many of you know, is a leader at RIKEN, as well, of course, as his previous academic institution, Tokyo Institute of Technology, and is a driver of the work being done on the Fugaku computer. Now, he and his team helped me a great deal, try to pull together information, and due to lack of time, I can only touch on some of these. But Japan has pulled together under the HPCI, the High Performance Computing Infrastructure Initiative, a number of tier 2 machines across their country into an aggregate by grids of over 200 petaflops worth of computing. And frankly, it's probably better now from the point of time. And as you will see, this is a repeated story and has done so by eliminating the usual bureaucracy in making awards to researchers who can help. Excuse me, I beg your pardon. No, this is not product placement. They have made it possible for researchers to jump on this with no cost assumed to the researchers in order to use the systems for making the cycles available. At the bottom of the slide, there are just 3 examples, and I had access to more than a dozen such examples that are ongoing right now. You just get the tone of this, and this is The first is exploring new drug candidates for the COVID-19. And this is being done on Fugaku. I'll talk a little bit more about Fugaku later in this presentation as well. Prediction of conformational dynamics of proteins on the surface of the SARS-CoV-2, again using the Fugaku machine. And if I've learned anything from putting this talk together, it's the word conformational, and I didn't know what that meant. And simulation analysis of the pandemic phenomena. Now, the reason I picked these three out of a much, much larger set is because they define the dimensions of the challenge. Ultimately, we need a drug, we need a vaccine. Only then can we defeat the pandemic with confidence, and we're nowhere close. Some people are very optimistic. I hear claims that even perhaps by the end of this calendar year. I'm not sanguine about that, but what do I know? But we also see treatments being developed as well. And then understanding the underlying mechanics of how the virus is working must be studied in order to understand how we can develop and construct approaches either to treatment or to a vaccine. And then finally, understanding how the pandemic phenomena transmits. And it had been very peculiar. Here in the US, on the West Coast, we saw the first few cases, principally in the state of Washington, Seattle, an example of this. And this is anticipated that it came through principally traveling from Asia. And then towards the latter part, New York City became the hotspot for the US and pretty much retained as much for most of the last few months. But it didn't get it from Asia, it got it from Europe. Now, I'm not a microbiologist or a geneticist, but those who are able to track the small perturbations in the different viruses to be able to track their migration. So Japan is taking a truly aggressive approach, and part of this, of course, is the scientific creativity. Part of this is the availability, the integration, and the application of a large number of resources that they have been developing over many years. And part of it is defeating the typical problems of bureaucracy that we all have to face all the time. And I congratulate Satoshi and all of his many colleagues on this. Germany, and in this case, I'll talk about the Jülich Supercomputing Conference. My thanks to my friend Bernd Mohr, and as well as Thomas Lippert and Daniel Rowe and others for information that helped. And it's a similar story, but with one addition. Europe has come together under the framework, the infrastructure of PRACE, and has used that as a mechanism for identifying and selecting and quickly applying systems to different researchers, principally throughout Europe, although there are some additional collaborations beyond that. And in addition, and Jülich is a premier center, and I'm going to mispronounce them, but it looks like Eureka and Jules and, is that Joseph? I don't know. Parents, let me know. Are among the machines available in Jülich that are being made available to researchers. And once again, through the PRACE mechanisms, which other centers are also using, they are fast-tracking these awards for computer time to researchers and at no cost. In addition, the Jülich Supercomputing Center is providing computer science talent to help with the code development for its optimization on parallel systems, and for the visualization of the results for rapid understanding of the meaning of the computing work. And here again, I've just picked 3 of many different projects which are already underway on these machines. And again, here's one: the effective and efficient application of deep learning models to be able to do pattern detection of the X-ray images. Second is searching for inhibitors at the molecular level that are effective against the virus. And then a completely different scale is the screening study to investigate the docking of small molecules to the SARS-CoV-19 protein. And these, again, touch on many different dimensions of the problems that we're facing. Thomas Schultes, again, thank you, Thomas, who leads the CSCS, the Swiss National Supercomputer Center in Lugano, Switzerland. Hint, hint, I've never actually visited there, but would like to. Also is taking advantage of the PRACE infrastructure. These are different centers that may have been perceived as competitors, friendly competitors, instantly working together. Here, their flagship system is a Cray 40/50, a combination of upgraded machines put together. I don't know how to pronounce it. I know I should, but certainly PIZ-DENT, did I get that right? PIZ-DENT was one of the top 10 of the top 500 machines when it was first deployed. I haven't checked the list today. And here are 3 problems as well: the characterization of COVID, the envelope with regards to the small membrane protein. Second problem, accelerating the exploration of molecular and dynamical recognition and inhibition mechanisms, getting right down there to the molecular processes that are taking place. And again, as before, here is a drug discovery project against the main protease. And yes, I had to look that up too. Now in the US, with which I'm most familiar, a number of large computer centers, and I'm not doing justice here, but I'm just identifying 3 major ones that are working, have dedicated much of their resources. And these include the TAC, or the Texas Advanced Computing Center. You know, Dan Stanzione is leading that, and thank you, Dan, for your help on this. And Barney McCabe is chief scientist, maybe, Oak Ridge National Lab, which has been the host of the previous #1 machine for a couple of years, the Summit computer, developed by IBM and NVIDIA, and NCSA, whose earlier large machine, Blue Waters, has been updated since then. Okay, so I'm not going to talk about all of those. I will, at the end of my presentation, bring up a bit of work that we're doing at Bloomington, Indiana, at the Indiana University campus, where I'm from. I get to, show some brag rights here. So TAC's aggressive, and the word is appropriate, response to the COVID has been bringing up, in just a matter of weeks, more than 40 active projects on their machines. And these are, as this is supported in part by the NSF, these are projects from NSF, from CDC, from the Department of Energy, from DARPA, all related to the COVID responses. And TAC had been involved in participating with the Office of Scientific and Technical Programs on the COVID-19, an HPC consortium, bringing the needs of the scientific computing to the resources of the computational community within the US. And they too have made, have really short-circuited the process in getting a proposed scientific project onto the machines, literally within days. They're participating in the National Science Foundation's rapid proposal process response, which is contributing to making this possible. In fact, on the order of 1/3 of all the resources, both people and computing resources at TAC in Austin, Texas, are being applied to fighting this terrible disease. My congratulations to them and the other centers around the country which are doing this. In the area of problems, you'll observe here that there are many different problems. Oh, the machine you see in that postage stamp in the upper right is Frontera, their latest machine that has just been deployed. They're modeling the structural aspects of the whole virus, and they're doing screening for the drugs. And in the genomics, a number of other projects have been ongoing to understand, again, the foundational mechanisms that cause and duplicate the virus, which is part of the transmission process. Now, the very good work annually presented by Eric Strohmeyer of Lawrence Berkeley National Labs to represent the evolution of our field over a couple of dozen years from more than that, actually, excuse me, for the top 500 list using HPL or the high performance LINPACK, or is it highly parallel LINPACK? Sorry, Jack. Benchmark. And we get a very good picture. It's a wonderful database that allows us to see the sort of capacity or capability, if you will, of our field moving over. I love this database. It's wonderful for mining. Of course, there are different workloads that may require testing and stressing of other parts of the system. In that sense, LINPACK is somewhat friendly, focusing principally on floating point units and arithmetic logic units. And as the machines get larger, the matrices get larger, and there are order n squared and order n cubes, all which make everything somewhat nicer. Unfortunately, it also increases the time, and some people have predicted that the death of this benchmark, which has been so important and had so much impact on our field, may be that no computer will be reliable enough to stand up on this. My colleague, Dr. Maciek Brodowicz, originally from Poland, has worked with me to expose an aspect of this data that clarifies a very important distinction that can be not intentionally obfuscated, but can be confused about the standard chart that Eric shows between the #1 machine in the world measured by LINPACK and the number 500th machine. And we recognized that, in fact, there isn't a continuum of capabilities across those two orders of magnitude, which is roughly what it is between number 500 and number 1. But rather, it's highly polarized, where, as you can see on this chart, the top 500 rank is on the horizontal axis, and the machines are ordered from right to left in the lowest performance up to the highest performance. And what you see here is that, or at least we assert, that there's kind of a three worlds model. There's what we call the mainstream, which is that almost flat horizontal line that covers most of the graph. It's the leadership machines, which is that essentially vertical line way at the left. And then there is these a small number of additional machines that kind of fit between there. But the big take home from this is almost all of the computing that almost all of us get to do is along that horizontal line. It's the mainstream. And while we put a lot of focus attention on that vertical line, it represents a very small percentage in numbers, in counts, within the top 500. It does consume a disproportionately large amount of the total aggregate performance. If we take that data and we look at it a little different, we see that the mainstream computing, the number of machines on the mainstream computing is almost flat. And this is just over the last decade. This doesn't go all the way back. You also see that the leadership machines, the number is well within the top 10. And this has been continuously. So the top 10 machines are where the leadership computers reside, and they certainly don't reach out further than that. And then somewhat varying is this middle area that goes roughly between a factor of 10 and maybe something like 70 or 80 across the years. I also point out to you that on the right-hand side of this, for all three, the numbers are really flatlining, which is interesting. And excuse me for the repetition here. Again, this is the numbers in terms of R max for those three regimes of computing. What I take away from this is, if you put your fingers on two different points, that it takes about 8 years for a machine that would be number one on the list to slowly migrate down to number 500. You can do that exercise yourself. So the lifespan of a machine is about 8 years. Many machines don't survive that long because while they do provide that performance, there are other normalizing factors, not the least of which is operational cost and the value of floor space, which could hold a lot more performance. So we tend to roll them out faster than that. So it's my sad duty to, but certainly a responsibility to note some of our colleagues who have passed away, people who have contributed throughout much or all of their careers to our field. I was kind of lucky last year because there wasn't anyone that I knew about across the world that I had to identify. Not so this year. Maybe they travel in bunches. We're in a virtual world, so this is not so obvious over this week. But if we were all in Frankfurt together, wandering the halls, attending the meetings in the meeting rooms and the various parties taking place, or just meeting for drinks at the Marriott and equivalent, you would sense something was missing. The sort of absence in your peripheral vision, something that was always constant and is not. And that's our friend and colleague, Rich Bruckner, who only within the last few weeks passed away at too early of a young age. Rich is best known for his running of the information source inside HPC. And perhaps less so, he also started inside big data that covers a slightly different area. Rich had many positions within the field. He was very knowledgeable. He worked with Cray, he worked at SGI, he worked at Sun Microsystems, among other things. But over 10 years ago, his true interest, his true love was communicating, bringing information together, and then disseminating it in a more meaningful way. If you had to describe Rich, you would use the same phrase. He was the guy in the red hat. What a wonderful act of branding. And sadly, that red hat is no longer there. I took a few pictures. Rich, in the upper right-hand corner, you see Rich. Rich was a friend to so many people in the field. He was perhaps a point in which we all shared a common individual personality. And this is with, if I recognize it correctly, Carolyn Devaney, president of Data Vortex Technologies, Inc. On the lower right this is how I think of Rich. Almost always when he and I were talking, he was holding a microphone into my face. But there were many times when you could just interact with him casually, sitting at a small table or in a group of chairs, and he was never noisy. He had an endearing laugh. He never dominated, but he influenced the path of conversations, and he added to the richness of our field. I spoke a couple of days ago with Doug Black, who is taking on much of the responsibilities of Inside HPC and has promised me that it will go forward. And I told him that he should feel comfortable reaching out to any of us in the field where he wants some input, that in my opinion, all of us would help him. This is Inside HPC, and the work of Rich Bruckner complemented, did not compete with HPC Wire, Tom Tabor, and John Russell and Tiffany, and provided a different flavor, a different form. So it is sad that we will not see him again, but we will continue to experience the impact he had on us over the last decade and more. Some of you will know Anne Redalf. And again, an early passing. Anne was a polymath. She had many interests and was educated in a number of different fields. Natural sciences, her public affairs, ability to communicate, and that included helping to organize, in which she did many things throughout the community. And of course, HPC. She worked at the San Diego Supercomputing Center for some years with Fran Berman at UCSD, University of California, San Diego. She served as a deputy director of the Cornell Theory Center in Ithaca, New York. She engaged with Tabor Communications, Inc., including HPC Wire, but made other contributions with them as well. She was a strong advocate and a key player in women's and minorities' rights in science, in STEM. And she provided true leadership in the National Science Foundation's National Partnership for Computational Infrastructure, known as NPACI. Again, we benefit more than we will remember her many contributions, because her impact will go on indefinitely as she has helped our field mature in many different ways. Steve Tuke, I have to be honest, my path never crossed with Steve's. And this is really surprising. He spent 10 years at Argonne National Lab, and he was one of the 3 founders of globalist grid computing and a pioneer. He was a systems software architect, both at Argonne and at the University of Chicago. And Univa, which is the industrialization, not for profit, was the CEO and the chief technical officer as well. He was recognized at a very early age by MIT Technology Review as one of the top innovators under 35, and also by InfoWorlds magazine as one of the top 10 innovators, and this in 2003. I am told he was a delight to work with. He was energetic, always smiling, a great sense of humor, but a commitment and a conviction and a level of effort rarely equaled by others in the developing of useful software environments and tools that has importantly expanded the Globus community and grid computing. And for me personally, this is sad. I only just learned within the last few days that Lucy Knoll passed away. Now, for those of you in the US and involved in HPC computing, you knew Lucy. She was a person of singular value in our field. And she exhibited a personality that is remembered for her professionalism, really strong professionalism, and her passion for not just the field, but for the value of the field, and her ultimate integrity. You couldn't fool Lucy. I had the pleasure of interacting with her over a number of years, as she was before her retirement, she was a program manager at Department of Energy's Office of Science Oscar program. And I interacted with her frequently in that regard. Prior to that, she was at the Office of Cyber Infrastructure at the National Science Foundation. And yet before that, the Pacific Northwest National Laboratory in eastern state of Washington. She served as the Department of Defense program manager. And earlier than that, she was a professor at Lindbergh College in Virginia. She was a professor of computer science, and I think eventually headed that department. But if you knew her well, you knew that her first love was theater. She was engaged in theater at an early age, which made her truly, and she brought a very rich perspective, not a single dimensional perspective, but a rich perspective. And she had a wonderful sense of humor and a laugh that I can still remember. Lucy, we will miss you. But we have a field that is constantly growing and moving forward. The Ken Kennedy Award is given to my friend and colleague, Jeffrey Fox at Indiana University here in Bloomington. Indeed, he is my next door neighbor, although he doesn't really hear me much because, well, the houses are very far apart, but he's right next door. He received, let me just say, and knowing Jeffrey, he worked closely with Ken Kennedy over a number of years, and even when Jeffrey was at different institutions, certainly some of his seminal work was done at Caltech. He received this award for foundational contributions of parallel computing methodology, algorithms, and software, data analysis, and their interface with broad classes of applications. He has been a strong, vocal, and convincing advocate for data analytics and the new methods of doing them through machine learning and other other techniques. He's the director at IU of the Digital Science Center. No, this is not a computer center. We do have that as well. This is bringing the means, the algorithms, the methodologies for practical exploitation of parallel computer for this. He is a fellow of the ACM and a fellow of the American Physics Society. This year, not unlike others, the ACM Turing Award, I hate to say this, but it's like the Nobel Prize for computing, is shared by Edwin Catmull and Pat Hanrahan for fundamental contributions in 3D computer graphics and revolutionary impact of these techniques on CGI. This is very important. A few of you in the virtual world will have remembered the first supercomputing conference. It was held in 1988, and it was held in Orlando, Florida. And the keynote address was given by Seymour Cray. Why do I mention this? And that was because the theme, you'll recall, each supercomputing conference has a theme. Its theme was scientific visualization, very first theme of a supercomputing conference. And the techniques and developments of both Edwin and Pat were strong. Edwin was the former president of Pixar and Disney Animation Studios, and Pat was a professor at Stanford University, and their impact was significant. The Seymour Cray Award was given to David Kirk. A number of you know David. He spent much of his career at NVIDIA, serving both as chief scientist and as the vice president of architecture. And he is a fellow at NVIDIA, though retired from NVIDIA. He received the Cray Award for outstanding leadership in the development of GPU computing and in engendering its rise to the mainstream of HPC. I know David. A few of you will remember, I think it was in Hamburg, but I may have that wrong. David and I took the stage together in a point-counterpoint conversation, debate. I shouldn't really bring it up because, well, he won and I lost, but it was good fun, and it was very very interesting. And this was a highly deserved award. And he is a member of the National Academy of Engineering. And finally, Chris Johnson was awarded the Sidney Fernbach Award for outstanding contributions in pioneering work, introducing computing, simulation, and visualization into many areas of biomedicine in particular. Now, biomedicine is an important application area, and he's made significant contributions. But many of you who know Chris know that his impact is far greater over many fields. He is a distinguished professor of computer science at the University of Utah and a former director of the Scientific Computing and Imaging Institute. He's a fellow of the AAAS, of the IEEE, and of SIAM, and he's an NSF Presidential Faculty Fellow, and my congratulations to Chris. So I can't go through this without at least talking a little bit about a machine. And if I were to be paying attention to a single machine that has come online recently and is setting the direction for future computing, it would be the Fugaku computer in Japan. And you will have been hearing about this probably throughout this virtual conference. Personal opinion, I think the Japanese build wonderful computers. from the point of view of the engineering and the balance of these machines and the attention to detail, I remember going back as far as the Earth simulator. That was a 40 teraflops machine, really leapfrogged the rest of the community well more than a decade ago. And, you know, they built the building around the machine. The building itself was the case, but many since then. Those of you who have had the opportunity to work on K, K is in Kyoto, and I've had the pleasure of seeing it. That machine, again, beautifully balanced. And while it may not have been the #1 machine measured by LINPACK, it performed other application areas much better. For an example, it was the #1 machine on the Graph 500 benchmark, put together by my friend and colleague, Rich Murphy, and many others who contributed to its definition. In Fugaku, this is the machine that I would claim was redesigned and pretty much from scratch. Now that's not 100% true. It does use an ARM CPU and many core at that matter, for that matter. But this is on a chip and a framework that provides very high bandwidth and very low latency, at least among the local parts, and a very high bandwidth and rapid switching network on the chip and the scalability. In addition, it has a custom-made accelerator, a processor, sort of GPU-like, the SVE, which is designed by Fujitsu, and is added both speeding up both integer and floating point at different speeds, including its own cache, and very tight packaging, as well as massive memory bandwidth in and out of the accelerator. This machine is not just for numeric computing. It is not just for graph computing. It is designed in particular to be able to advance the capabilities in artificial intelligence, including but not limited to machine learning. And one of an exceptional note, is that because of the COVID-19 crisis, Matsuoka at RIKEN and his colleagues expedited the deployment. Originally, it was supposed to be deployed next year in 2021, but part of the machine, at least, has been deployed now and is running science applications targeting the COVID virus even as we speak. I put up for completeness this block diagram. I think the value of this in particular is that it exposes the data paths and the very high bandwidths and tight coupling that the Fugaku machine demonstrates and its design. It is a successor to the principles of quality of design and operation that has been manifest by Japan, RIKEN, MEXT, and others over multiple decades. Now, as I come to a close, there's an observation I'd like to share with you. And it's one that I think is because of the current world conditions, but also in response to it. I hinted before that we have, in fact, drastically reduced what appears a typical friendly competition throughout our field, sometimes national, sometimes different approaches and so forth. But I'm seeing a convergence, I'll call it a grand convergence, in which different aspects of our fields are finding that they have connections to other aspects. First and foremost, we represent high-performance computing. But what we're finding is that high-performance computing is really can be applied to and rapidly expand the capabilities of artificial intelligence, at least as understood as machine learning and supervised and unsupervised, and deep learning. Forgive me, I'm sorry. I usually consider them the same thing. And these further are converging into the worldwide challenge of world health applications in attacking, but not limited to, COVID-19. So we have computers, we have certain class of algorithms and models in AI, and we have the needs of humanity all coming together in this grand convergence. And we see innovation across the field in architecture, in the methodologies that we apply them, and in the new algorithms that define and describe how we use them. And indeed, in AI, the meta algorithms, algorithms that essentially allow computers to learn the algorithms they need to solve real problems. And here, recently announced completion is the IBM True North neuromorphic computing. It's a non-von Neumann architecture. It is digital, and there are other examples of neuromorphic computing that is analog. This is, by their claim, bigger than anything else ever developed by more than an order of magnitude. It has 1 million neurons, or let me rephrase that. It emulates and exercises 1 million neurons. And with that, yeah, I know I confuse you all with changing from base 10 to base 2, but it represents 2 to the 28 synapses, which are individually programmable. I don't exactly know what that means, but this is a spiking computer. That is to say, there is a representation of what a neuron does at the body. The input signals from the dendrites onto a neuron collect and slowly dissipate, but there's this aggregating algorithm. And if certain thresholds, which themselves are changing continuously, are crossed, then the neuron will fire or trigger, sending a spike down to its synaptic junctions and to other neurons. This is a very, very large chip, more than 5 billion transistors, not quite the largest chip in the world, but very close. I think it may be IBM's largest chip. And yet, the power it consumes on average is much less than a watt. In fact, less than 100 milliwatts. Now, one of the things that we are noticing, we're observing as part of this grand convergence, even as we come closer and closer to that moment, that milestone of exascale, we are in fact broadening rather than tightening our shared definition of what exascale is. Yes, we know what Rmax exaflops is. That's measurable, and at some point, some machine will hit that. If not this year, next year. In fact, it may have already happened. But what we are learning is that computing operations are far more than double precision floating point. We are, in fact, recognizing that precision wasted is really not precision at all. And for applications like machine learning and deep learning, the numbers that we need really can be much smaller, 16-bit, for example, numbers. And so instead of a 64-bit floating point add, we can handle many operations in the same time that we would do one of those. And having done that, it's quite likely that if we're measuring certain kinds of operations per second, that we may be already crossing the exaops boundary or numerical boundary or intelligence boundary. And so there's a much broader array of ways in which we can achieve and exploit exascale. Now, here's the tough one: 50 giga synaptic operations per second. Okay, I'm guessing that this is actually the measurement of transitions from one neuron to another neuron, and each one of those little connections at the synaptic junction is counted as an operation. Now, the architecture is such that there are many neurons in what is organized as a notion of core. There are about 4K of these cores on a chip, 28 nanometer feature size, so it's not, they're not pushing the edge of technology. And each core, not neuron, each core has about 400 kilobits per core. That manages to hold the notion of what a particular neuron is and capable of doing, and the local information representing the state of the neuron at any point in time. This neuromorphic computing, this is a major step in advancing what is still a speculative approach. There is no doubt that neuromorphic computing will be able to perform certain classes of operations like pattern matching and associative searching much faster than typical digital conventional techniques. But it's also probably true that we don't actually understand general purpose computing with neuronal structures, although all of us, within about 1,450 cubic centimeters and operating at 20 watts, all of us are using on the order of 89 billion of our own neurons to be able to do things that for us are trivial, but for computing is very, very hard. And I'm not talking about playing Go or playing chess. I'm talking about deciding whether or not to take an umbrella out into the common sense challenges. So this is a milestone in a future that is exciting but unpredictable. I close where I started, and that is the challenge that we face worldwide in terms of health. And one of the important things is not just how to attack one virus or another, but it's to understand using machine learning techniques, how to computerize the state of the health of humanity on the individual. This is referred to as precision medicine, and to a significant degree is the translation of images of many, many different sorts, X-ray images and CAT scans and MRIs and so forth, and being able to correlate them as they relate to both diseases that have been learned from in the past and therapy solutions. And my institution, Indiana University, is one of many that are developing new state-of-the-art techniques to push forward precision medicine. We have a program called the Precision Health Initiative at IU. And there's much more work being done within the US and worldwide in this important area, and very important because of what we're facing right now. And finally, within Indiana University, within the School of Informatics, Computing, and Engineering, and within the Department of Intelligent Systems Engineering, my colleague Paul Macklin, which well known in developing techniques, including but not limited to AI techniques and simulations, and software infrastructure to be used by many other, has developed a framework called PhysiCell, which is designed both with advanced techniques in modeling large cells, but also with infrastructure interfaces for easy user application. In addition, and in collaboration with colleagues at Johns Hopkins University, he's attacking a number of different cancers through simulation techniques. He's also working with the University of Southern California on other colorectal cancer, for example, in this case. And something more subtle, and I don't completely understand it, is the notion of digital twins. And this is where you are in combination measuring physical properties of a condition and matching it with the computer model of the condition and allowing the two together to optimize and determine parameters of the model based on the actual physical condition. So there are these two different versions of the same thing. One synthesis, simulation, and the other the real case. And this is very promising. It's been used in other fields, but this is a first time, and Paul is leading that form. So I hope you don't mind me just bragging about one of my colleagues, but this is work that he is also bringing to bear on the challenges of COVID-19, using these techniques to model and explore some of its properties right now when it's most desperately needed. So I want to thank you all very much for viewing this. I'm a little uncomfortable. I like to see you. I like to picture you out there, 1,000 or more of you. I like to be talking with you, not giving you a canned speech. And I look forward, hopefully, very much to talking with you and seeing you in person next year in Frankfurt. Let me thank the sponsors of this conference, in particular, given the financial aspects of it. This could not have been done without you, and for those in the media who are helping to disseminate these virtual presentations to make them readily available to the broadest possible worldwide organization. I thank the organizers, the leaders of ISC 2020 for making this readily available, free of charge, so that the barriers are removed, eliminated. And I hope this means that many more students than usual will be able to benefit from this. And one last personal note, I want to convey my greetings and warmest regards to Ursula Maurer. It is always one of my great pleasures to meet her at these meetings. She is the mother of the International Supercomputing Conference Series. I can see her smile in my mind, and I truly look forward to spending time with her next year, assuming, of course, that I'm invited to speak again. Thank you all very much, and thank you for your time in going through the many presentations that others have worked hard on to make this remote conference a success. Take care, stay safe.